Thank you, Michael. Our first speaker today is Simon Guest from the University of Cambridge. Simon Guest is a professor of structural mechanics and currently head of the civil engineering division. His talk will be about the geometry of origami. Welcome.
It. And this. Okay.
Hello, thank you. It's a great pleasure to be here. I worry somewhat that I'm supposed to be inspiring. I'm not sure I can be inspiring, but I can at least tell you a little bit about some of the work that I have done in geometry and geometry relating to origami. I very much listened to the talk about multidisciplinary and interdisciplinary work, something that I very much support, something that the University of Cambridge Engineering has always been, I think, a good example, because we've always had a single engineering course. So my background is thinking of engineering as a whole. And so, although I'm currently head of civil engineering, I work on deployable structures, and I'm willing to be, to take inspiration from any topic to work on these subjects. And so some of what I do, a lot of what I do, is highly geometrical. And I'll give you, hopefully, a little bit of a flavor of that today. And in thinking about what to talk about to a fairly general audience, I decided that I'd give a sort of personal journey through my work on origami. And that means that the work I'm presenting is actually work I've done with perhaps the three strongest academics that I've worked with. So Sergio Pellegrino was my PhD supervisor. Mark Schenk and Zhehan Hui were both my PhD students. And really, everything I say today is really due to them rather than me. So in thinking of this as a personal journey, it gave me a good opportunity to go back to look over the three things, the topics that I'm going to talk about today. Firstly, about a thing called the wrapping fold pattern, which is my earliest work. Then we'll talk a little bit about the deformation of the Miura ori, which is probably familiar to many people here. And then also some work then that's really very much inspired and builds on work done here in Vienna with the great geometry work on looking at possible shapes of origami. So starting out with the wrapping fold pattern. And in each case, I'll try to mention a little bit to give a theme to the talk about how the geometry has been modeled in each case. So this was something that I did in my PhD. This was a way of folding up a flat sheet by wrapping it around a central hub that it turned out had been around, it's been suggested lots of times since the 1930s, I think, was the earliest example. And what I did was to explore the geometry of that sheet. And this was my first paper that I wrote, so it's been a great opportunity to go dig out these old pictures which I think are the only pictures that I have which were actually hand-drawn. So in terms of computer technology, this was right on the transition when from then on, computer technology, all the pictures I have are things being drawn with a package. But these are kind of hand-drawn on drafting paper. And although this was my first paper in 1992, I was really pleased to see the February issue of the National Geographic, where you see on the right-hand side exactly the same fold pattern is now being suggested as a way of something called the Star Shade Project. So the idea of the Star Shade Project is that this is, if you want to directly observe the light from an exoplanet, then what you have to do is you have to shade out the light from the star so you can just capture just 1 pixel of light from a planet. And this will be the idea. The idea is that this pattern would provide the shade for a space telescope. And potentially, if this works, you could do spectroscopy on the light, and if you can do spectroscopy on the light, you can detect oxygen, other molecules, and maybe you can detect life elsewhere in the universe. So it's a very exciting project, and it's great that it links back to the original work that I did on how to look at the geometry of this folding. And so looking back at this, I look back at actually, how did I approach this? So at that point, I knew very little about origami, about geometry. But actually what we did was essentially simplify the system, consider the flat shape and the folded shape that we see in the bottom right-hand side, look at the angles that allow things to fit together, and it turned out to be really a very straightforward calculation what the shape would be. This shape that I show here assumes that the paper has 0 thickness. This is a very common assumption in origami and is often a very good assumption to make. But in this case, the paper wraps around itself and the thickness builds up. So actually that assumption quickly becomes difficult. And so what we did was we instead considered what would happen if, as we folded the paper up, these folds gradually got larger and larger, and you end up with a slightly curved fold line. And essentially what we were doing here is that we took as the variables in what we were doing the vertex coordinates. So we fixed where we wanted the coordinates to be, and then we could solve for where those positions were by constraints on the sector angles, which in this case was just the constraint that everything has to add up to 2 pi. So you have to have a flat foldable sheet in the starting point. So this was a case where the geometry was specified by vertices, and summing up angles was the constraint we added. Lots of constraints we ignored. I didn't think about whether the facets were going to flex or whether this needed to be rigid origami or non-rigid origami. These were all terms that I hadn't really considered at that point. But really, I have an underlying engineering sensibility. And the reason that I thought this was good is because it worked, because it allowed you to fold up a sheet and allowed you to wrap it up and to give you a shape that was successful. Now, as an aside, this is the end of that piece. As an aside, I noticed when I was putting the talk together that one of the figures that we put in the paper was the following figure, which I think might be the first appearance of a Miura Ori in a paper that wasn't written by Koryo Miura. So we copied his figure because we wanted to talk a little bit about the constraints on origami and origami folding that Koryo Miura had expressed in some of his work in the previous decade. So this Miura Ori pattern, which I think many of us are familiar with, then provides a very nice link across to my second topic, which is work that I did with Mark Schenk about 15 years ago. Mark is now working at the University of Bristol. And what we were doing was to take a partially folded Miura sheet. So this was now thinking of the Miura sheet that you see here in the top left as being a sort of material, a structure, something that has got some properties. So we're not just thinking of it as being folded and open, but now somewhere in between. And also, we compared that with this thing which we call the egg box sheet, which is in the bottom right, which is very similar, as we'll see. But in fact, this is not a developable surface. So the egg box, the Miura sheet I'm showing here you see has got this very familiar fold pattern that we know about. The egg box has got those same patterns but arranged in a different way, and that means that you have vertices that have an angular defect and vertices that have an angular surplus. So on average, you don't have any angular defect, but you can't make it from a single sheet. And so here's a close-up view of those cases. So the work we were doing here was now quite a different piece of work. It was to say, if you were thinking of these structures, these folded sheets of structures, then they have some very interesting properties. So the Miura sheet is an example of a sometimes called an auxetic structure. So it's one where if you pull it in one direction, it expands in the alternative direction. This is something a little bit unusual, but by no means impossible, and indeed something that is actually, if you start to think about it, quite a reasonable property of a structure to have, even though all of the familiar structures we have behave in a different way. So it has this negative Poisson's ratio, whereas if we were to do the same thing with the egg box sheet, then you end up to find that you have a very positive Poisson's ratio, very much the kind of standard material response you might expect. So, firstly, we had that interesting contrast. But then the really interesting property of this structure is that if you now try to bend it out of plane, which, thinking of the folded sheet as a material, is a very natural thing to do. If you were thinking of this as some sort of structure of a roof, perhaps in geometry. And what you discover is that if you fold the Miura sheet out of plane, then you get this anticlastic shape. If you kind of defocus your eyes and look at the overall shape, what you end up with is this anticlastic bending, so the curvature in two different directions. And that's exactly what you'd expect from a positive Poisson's ratio. So exactly the reverse of what we saw in plane. And if we do the same with the egg box sheet, when you fold it out of plane, you get this synclastic curvature. So that's very much what you would expect with a negative Poisson's ratio. So we have this very odd situation, at least for me, it seemed odd that you have a material that you've made, a sort of meta-material, by taking an origami sheet and folding it in one way, or taking a sheet and arranging it for the egg box pattern. Each of them then have some emerging properties as a metamaterial. And those emerging properties are not the properties that you would ever get with a single standard material, because you have this reversal in effect of what the Poisson's ratio looks like. So what we're talking about today is modeling origami. So how do we model this? And we modeled this really in what seemed to be a very straightforward and simple way, but has turned out to be to give interesting results. So we simply thought of, in this case, we would model the structure as a truss structure. So we would have the vertices as being our pin joints, and we would have fold lines as bars, and we would add some extra bars to make sure there's no in-plane deformation. So here's the relationship between the origami and the truss structure. And now, if we think about what we're doing with our modeling, we're thinking about our variables as previously the vertex coordinates, and our freedoms are now the variables, the vertex coordinates, those are the freedoms. The constraints are that we just fix the lengths, some lengths within the surface. So we're fixing a set of lengths, and that then allows us to do very simple modeling something that is in mathematics often called rigidity theory, or it would be what our structural engineers would learn in their sort of first year engineering calculations, that you linearize the geometry of the structure. You look at a compatibility matrix between D, the deformations of those nodes, and E, the extension of the bars. And it's actually Jacobian of quadratic length constraints, so it's a straightforward thing to calculate. And if you look for the compatibility matrix where you have a null space, so where can you deform the structure while to first order not changing your length constraints, that gives you some mechanisms, infinitesimal mechanisms of the structure. And that's not going to be quite enough for what we have here, because remember we've added these extra bars. We haven't maintained the flatness of the facets. So we have to add in some additional constraints. And what we did with Mark was to add in angular constraints on the facets to make sure those facets couldn't fold. And again, we followed the same thing. It is the form of the constraint is not as simple as it would be for a simple length constraint, but you can calculate the angle, do the first order compatibility, and now our variables, those vertex coordinates, the constraints are the lengths of the bars and the angles for the facets. And if we put all that together to form a sort of augmented compatibility matrix, we're looking for the null space of this matrix. And what we find is really what you would expect. This was the sort of straightforward result, that the 1 degree of freedom motion that is allowable for each of these sheets, without really thinking too hard about the ultimate geometry, is that for the egg box, you get a standard positive Poisson's ratio. The deformation, you stretch it on one way, it contracts in the other. Whereas for the Miura sheet, here I'm showing compression. You compress it in one way, and you find it compresses in both ways at the same time. So that's the that's the in-plane deformation. The out-of-plane deformation, though, we have to allow. Oops, let me reverse this. The out-of-plane deformation, we have to allow some deformation of the facets, because what I showed earlier is the only way these structures can move. This 1 degree of freedom that's given by the special geometry is the only way the structures can move. But if you handle these sheets, and I noticed in the exhibition that I'm looking forward to later, you'll see that you can get these out-of-plane deformations. That relies on some facet bending. So to do that, we have to say that some of our constraints are now not really constraints, they're stiffnesses. We allow some deformation for these structures. And so what we did was we allowed some deformation of the facets. And we also, at the same time, gave the folds a little bit of stiffness, because maybe the folds don't fold completely freely. And it turns out that the way to generate a tangent stiffness matrix, which describes the stiffnesses of this structure, is very straightforward. And I'll just go back the slide now to calculate in terms of those earlier compatibility matrices I described. Very straightforward calculation to do. And that tangent stiffness matrix allows you then to look at how does the structure want to deform. So what we ended up with, we said we have very stiff bars, we don't want in-plane deformation, and we allow some out-of-plane deformation of the facets. And then we looked at what are the softest modes of the structure. And what we discovered is that the softest modes capture exactly the deformation that you might want. So the twisting and the saddle mode you see here both show this anticlastic deformation, which is the deformation that we were looking for. Whereas if we move on to the egg box sheet, the softest modes, the way the structure wishes to deform captures these synclastic sort of curvature modes that you want to have. So that was that was I thought computationally quite a nice result to have. At the same time, Mahadevan in the States has also done some related work on this, and it's become there are better theoretical descriptions of why you get this negative positive Poisson's ratio behavior for out-of-plane and in-plane deformation. But this was the modeling that we did with this sort of really simple geometry. But coming out of that work and actually described in exactly the same paper was a suggestion that a useful thing to do with Miura sheets might be to stack them together to form a metamaterial. So with Mark we built this. Mark noticed there was this compatibility in the geometry that you get between different Miura sheets, where however much you stretch them in the vertical direction, the in-plane deformation for the folding remains the same. And so you get this very interesting possibility of stacking up lots of sheets, and there were now lots of other ways of stacking up sheets in this way, and indeed this work has gone on to be used by companies looking to build soft foams for protective headgear and such. And so this was the in that same paper, the deformation that I showed earlier, this deformation of the sheet. And almost as an aside within that work, we also showed another way of stacking a set of polyhedra, and another way of stacking a set of Miura sheets. And this looks very much like the previous picture that I'd shown. But what you might notice is that one of the fold lines in the center has just been changed a little bit. And so this has been designed so that actually the structure will fold and will lock during its folding. So unlike the previous example, where the sheet had been designed that it would fold like a Miura sheet will do, fold completely flat, in this case it can't. It can't because there's this clashing that occurs. So in the middle, there's one of the fold lines has been deformed a little bit so that the deformation can't go any further. And this leads naturally on to the final topic that I'm going to talk about, which was the question that I originally set to my student Zechan Hay about, well, this seems interesting that you can produce these different sheets. What else can we do? You know, how else could you produce sheets that have this quadrilateral folding that might allow you to produce different ways of producing different shapes that might lock in different places? And it turned out that what I thought was a trivial question, not quite trivial, but simple question, coming out of this simple model that we've made, turned out to be really awfully complicated. And I'll try and give you a little flavor of the complications that we'll see in a moment. So my final topic is to talk about how can we fold up infinitely extendable quad sheets. So the basic question we have is that we have some sort of quadrilateral mesh. So we basically know how the folds are all connected together and how they join. They all follow this basic quadrilateral pattern, but we allow the geometry to deform. And in general, it's very easy to show that if you produce a sort of random geometry there, what you will end up with is a rigid structure. So the fact these structures can fold, the Miura folds that I've shown, and indeed this this special example of the Miura fold that locks during its folding, they are all kind of special cases of a quadrilateral fold. And this was then the topic that has absorbed Zhehuan for the time since I first introduced it. And the modelling that we're doing now is now much more geometrical. So it's basically what we do is we now think of the variables as being the fold angles for the structure, and our constraint is that the sector angles that we describe have to be maintained. So how can you have a system where you can vary the fold angles but keep the sector angles constant? And the approach that we reached here, after a lot of help from Ivan and other people in this room, is as follows. So the basic condition that we took was that we start off with our sort of folding pattern. And what you can do is if you sort of cut all of the facets into pieces in the manner that you see in the middle of the picture here, then you can guarantee that you will end up with a structure that will be foldable. So it's very easy to show that by cutting all the facets, you've changed one angle, you'll change all of the other angles. And the question we then have to answer is, how can you make sure that the pattern is such that the deformation you produce there gives all of the facets in such a way that they can be joined back together again? And so we came across this basic loop description that around each facet you have to have a set of angles that allows this deformation that had been introduced by Tachi and others a little bit before we were starting working on this. And the key thing about this is to understand for this loop condition, this Kokutsakis polynomial, that really, in this case, Helmut Stackel, I know, did some great work on this, but Ivan Esvestiev really did the very expansive work on understanding what the conditions were on the angles for this to be able to fold. And it's that gives you the loop condition that you can look at for possible shapes here. And what are the calculations you have to do, and something that Zhehuan has been working on lately, is to be able to know about what happens at a single vertex and look at the classifications of all the possible ways that a single vertex can fold. And it turns out there's a lot more depth to this than I ever expected. You then, once you know about how a single vertex folds, you can look at the possibilities of how you can stitch together Kokutsakis polynomials in such a way that we want to be able to say, firstly, every crease is folded. So we don't want bits to effectively rigid parts of the structure. We want this to be a general folding pattern that we can solve quadrilateral by quadrilateral in such a way that we have an infinitely extendable construction. And because we're really engineers and not mathematicians, we only want to have real solutions. So there'll be lots of solutions here that might work with complex numbers, but we want to actually be able to make the structures that we end up with. And it turns out, and I'm not going to go through this in any sort of detail, it turns out that there are lots of possible ways of solving this problem. And I'll go through, without describing in detail, the sort of series of them. So here are some of the possible results you get. So one possibility, which goes back 150 years, is the thing called the V-hedra and the anti-V-hedra. So this is a well-known possible solution to the problem, where there's another set of surfaces called T-hedra, T-surfaces. The The Miura Ori is an example of these. Again, this is something that goes back to the 1930s and has been well understood. But there are lots of other possible ways of doing this that my student Zerwan has come up with, and we have various names for them. This parallel repeating example. There's various other linear repeating examples. And so what you see is that actually this has turned out to be not a simple area at all, but an area that is awfully complex, where you can produce a lot of different variety. And this gives us, I think, as engineers, as geometers, as mathematicians, a great deal of material to work with for thinking about possible things that we might do. So possible things we might do, for instance, is trying to approximate surfaces with fold patterns. Here we have a sort of conical surface that we're trying to model. And also something else that Zerwan has come back to is the self-locking phenomena. How can you design these surfaces that fold? And in this case, the very end pieces of the fold pattern here have been designed that they fold around and lock the structure in the final shape that you might get to. So that was this recent work on geometry. So I reach my conclusion. And my conclusion is really, well, it's really a conclusion of looking about over the series of things that I've got here. All of these are examples of work that have been based on origami, where ultimately geometry is critical. Each of the applications have been in rather different directions, but I think this comes back to what we heard earlier, the necessity of being able to work across disciplines, of being able to work in a multidisciplinary way, because the ultimately underlying tools here are geometrical tools applied in very many different ways, and it's been a really interesting journey to see this work develop. So, thank you very much for listening.
Thank you for the interesting talk, and now it's time for questions.
Thank you for the presentation. You talked a little bit about the actual thickness of rigid origami.
Yeah.
And now you showed lots of zero thickness origami, and I was wondering, do all these patterns also work if you have actual thickness?
Okay, so most of the work that we've done has been to assume that there's no thickness, except for the wrapping, where the build-up of the material implies that you have to consider that. The last piece of work we were doing with Zerwan was all about rigid origami, because if you allow facets to bend, you get a lot of different possible solutions. Now, if you then want to build a practical structure from these, it very much depends what the structure is, whether the thickness is something you have to include or not. So if we were, for instance, considering the design of a roof structure where we want to think of the fold pattern, like a Miura fold pattern, as being the overall structure of the roof, then the kind of thickness doesn't really get in the way of the description that I've given here. So therefore, the thickness wouldn't matter. But if we were wanting to fold up a structure whereby, for instance, the work I described with the self-locking, where it absolutely would matter, the contact between one piece and the next. So it's really a case-by-case basis. What I've described here has not included looking at thickness, but there are all sorts of interesting work to be done, looking at the detail of how, which of these solutions allow allow you to design a structure where you can sort of put some thickness around this theoretical surface that we work with.
Thank you. Maybe I can add something to this. We were asked to design a kind of Miura origami for a shading system in our city to span it over the river. So it should have the size of 10 by 10 meter. And then, of course, the problem of the thickness appears because you need a kind of frame for all the quadrangles and so on. And we worked together with structural engineers. And at the end, I think we found a solution. But the only problem was there's the island in the Moor. This is a building which was built 20 years ago, and this has a freeform shape consisting of triangles. It was translated in triangles, but we had the quadrangles for the origami, and so the architect didn't like the solution, so we had to skip the work. But it's always the problem if you make a bigger structure, then you need a kind of thickness to open and to close the system, and then already with the origami pattern, which is an easy pattern, problem appears.
Yeah, absolutely. If you want to build the practical systems, but actually the Miura, one of the very first description of it was as a design for a folded map. But Koryo Miura was a space engineer, and that's how we knew him. And he was wanting to use this pattern to design folding panels for a solar power station. And so actually the thickness was an important consideration. And there are games you can play to add the thickness around this theoretical underlying surface. But it's something that absolutely has to be considered for many practical cases.
So I have a small follow-up question. So you said the Koryo Miura design of this solar panel, so it was actually non-zero thickness. Is it free source or is it patent protected? So how he did that?
I'm pretty sure it wasn't patent protected, and even if it was, the paper was written in 1985, so the patent would have died a long time ago.
Thank you for the interesting presentation. You have mostly spoken about rigid origami, as you said, but you have also underlined the importance of taking flexibility of faces into account. So I'm coming from mechanics, and I'm interested in this part of your simulations. Was it kind of finite elements, plate finite elements, which you used for modeling this flexibility? And if yes, how did you in general ensure the continuity conditions on the edges between those faces?
Yeah, no, it was a sort of bespoke piece of computational package, which was essentially modeling it as a truss structure, as a simple description of the compatibility matrix, which we augmented with facet bending. So the package we used just a linear algebra package so all of the continuity was built right in. It wasn't, we weren't trying to use a package outside to be able to model the behavior. It was a much more simplified system than that.
Thank you.
Maybe a related question. When you consider the out-of-plane bending of these sheets, your model assumes that there are these secondary folds along the diagonals of these. But in general, so is it reasonable, that's the first question, to assume this? Are there such folds in an experiment? And if yes, each quadrangle has two diagonals, so how do you choose the correct one?
Yeah, so that's a great question. Again, I would appeal to the, maybe this is kind of an engineer rather than mathematician speaking, I would appeal to the fact that the results of the calculation captured the behavior that we saw in practice. So in a sense, there's the anchoring with the reality of the structure we saw is a validation of the approach. It is absolutely true that what we did was a simplification. And it is certainly the case that if you want to add bending to a quadrilateral facet, there are two diagonals you could choose. What we did is we chose the shorter diagonal because that felt like the most flexible way that the structure would fold. I suspect, but I don't know, I suspect that had we chosen the other one, we would have got essentially similar results. But I can't guarantee that because maybe we got an answer that looked like what we expected. And as an engineer, that's what we wanted. But maybe we should have got into more depth.
Any more questions?
Hello, thank you for the presentation. I was wondering, you mentioned that the layering of the Miura sheets into a sort of metamaterial struck the interest of protective headgear manufacturers. I was wondering if there were, to date, real-world applications for a similar product, but with the locking fold.
Yeah. The answer is not as yet. So I'd like to hope that it would indeed be, because what that potentially gives you is with something like a foam structure that you can engineer, you could have an initially soft response and then a much harder response, which might be exactly what you want in a crash protection situation. So I think there would be good applications, but they haven't appeared yet.
Thank you.
If there are no more questions, then let us thank Simon again.